Our last topic in section 10.2 is not very difficult, but it's very useful. We are going to use this a lot later in chapter 10 as well as chapter 11. So you might as well highlight it and put a star next to it, because boy, are we going to need this topic. It's the growth rate of sequences. Very big deal. Deceptively big deal, because it seems like such a small thing that they tucked it in at the end of this section, but we're going to use it repeatedly. All right, now before we go any further, I don't know about you, but when I was taking some of my standardized exams in high school and, those kinds of things, I kept seeing exclamation points after numbers, and I never knew what the heck that was. So I'm sure I did not pass those particular portions of the exam. What it means is factorial. So when you see n exclamation point, what it means is you multiply 1 times 2 times 3 times 4 times 5 times 6 times 7 all the way up to n. That's it. That's all it means. And I wish somebody would have told me that a long time ago. And also, by definition, 0 factorial is 1. I don't want to get into why, just suffice to say that it is. There happen to be some combinatoric reasons for why it has to be that way, but 0 factorial is 1. All right, so 4 factorial, just for starters. 4 factorial is 4 times 3 times 2 times 1. I tend to go backwards. I tend to start at the 4 and then work my way down. Although it's written up here as I'm working my way up, it doesn't make any difference because multiplication is commutative, so it matters not. This is 24. Now, could you find it with Desmos? Why, yes, you can. Right? Computers and calculators know what the exclamation point is, and there you have it. Oh, not 24. My goodness. 4 factorial. There we go. It's 24. See? What computers and calculators cannot do for you is ones that involve letters, but we'll get there. All right, so 14 factorial. 14 factorial will be 14, 14 times 13. My hand nudged the mouse. Times 12. Now, I'm not going to write all the numbers. So we just assume it continues in this vein until the last numbers, which are 3 times 2 times 1. We are so not going to find that by hand. That is what Desmos is for. So if that was part A, 14 factorial, there we go. So I'm just going to put an approximation sign. It's 8.718 times 10 to the 10. Lovely. All right, now what about 2 times 3 factorial? So what they want you to understand here is that factorial is kind of a grouping symbol. So when you have 2 times 3 factorial, what that is 2 times, and the factorial only works on what's right in front of it. So that's 3 times 2 times 1. Sorry, my colors aren't making it obvious enough what's going on here. So that's 3 times 2 times 1. There we go. Now you can see the difference. As opposed to this parentheses groups together. Oh, I didn't even bother figuring out what this was. 12. Right? 4 times 3 is 12. All right, so, but this one is not. This one's much larger because what's happening here is because of that parentheses, it's grouped together. 2 times 3 is 6. So this is 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. Right? Which, of course, I could find with Desmos, although it's 30 times 24. But I can just type it in, and the computer will tell me it's 720. Now, computers are all well and good for numbers, but again, they're not so helpful with the letters. But I wanted to do these examples so you could see, because this is where we're going to really need this. So as I told you, this stuff is going to get used later on in this chapter as well as chapter 11. So I want to make sure you understand the difference. This one on the left is 2 times n factorial, right? So what it is 2 times just one number 2, and then it'll be n times n minus 1 times n minus 2 times so on, so on, so on, times 3 times 2 times 1. I don't know why I put 3 in parentheses there. I get so used to using parentheses, I guess. Right? So one number 2 times all of it. As opposed to this one over here, which is really 2n times the next number down, right? 6 times 2n minus 1, which was 5 here, times 2n minus 2, which was 4, and so on and so on and so on until you get to 3 and 2 and 1. See the difference? Actually, this is a much larger number than this, right? Because this has the 2 times the n factorial, whereas this is only 2 times n factorial. So this would be a smaller number than this one. Right? You can see it right there. 12 was smaller than 720. They weren't even close, right? This is 2n factorial. This is the quantity, 2n, close that quantity, factorial. Much larger, much, much larger. All right, now let's look at the squeeze theorem for the sequence negative 1 to the n over 1 over n factorial. I told you that the negative 1 to the n ones, that's very common for them to be used with the squeeze theorem. So step 1. I need to find 2 sequences that bound this sequence. I don't know about the squeezing part, but I know that I want b sub n, which was negative 1 to the n times 1 over n factorial, to be less than or equal to one sequence, but greater than or equal to another sequence. Well, it's pretty obvious. I'm going to pick a sub n over here to be the negative values, right? Because negative will always be less than or equal to this. And then I'll pick c sub n to be positive 1 over n factorial. Again, because this negative 1 to the n piece in here is as high as positive 1 and as low as negative 1. So as long as that's the case, then this is true. Okay, so step 1 is done. I found 2 sequences. Now step 2, I have to prove that those 2 sequences squeeze. So I need the limit as n goes to infinity of a sub n, which is the limit as n goes to infinity of negative 1 over n factorial to be something. And then I need the limit as n goes to infinity of c sub n, which is the limit as n goes to infinity of positive 1 over n factorial to be the same value. So I need these to go to a value, and I need them to be the same. Now, are you thinking about what this value must be? Hopefully. All right, so here they are right here. So here's 1 over n1. So there's my c sub n right here. I've got it in blue. And there's my negative 1 over n1 factorial, and that's my a sub n. Do you see where these values are going? Do you see how small these are? That's scientific notation, so it's 0.00000002755. In other words, it's going to 0, right? You can see it. Because, of course, think about this for a second. Infinity factorial. Take infinity, multiply it by infinity minus 1, then infinity minus 2, then infinity minus 3. This is a huge number. This is absolutely monstrous. This is negative 1 over infinity factorial. That's negative 1 over infinity. That's like hella infinity. That's like super, super big. So that would be 0. And similarly, this one is positive 1 over infinity factorial, which again is hella large infinity, which is 0. But then we've done it. We've squeezed, right? We've got our squeezing part because the 2 limits are the same. The limit of as n goes to infinity, I want to change my color here. Sorry. Well, I'll just leave it. I'll leave it. The limits are the same. They're both 0. And since they're both 0 and b sub n is squeezed between the 2 of them, that means part 3, therefore that the limit as n goes to infinity of b sub n is 0 also. And I can prove it. Well, proving is hard to say. It's not really proving it, but I can numerically kind of show it to you looking at this value, right? So it's all the same numbers as the other 2, but it's positive, negative, right? The negative one's always negative. The positive one's always positive. So the blue one, always positive. The red one, always negative. And that black one is alternating between the 2, but it's squeezed in between them. And since they're going to 0, and they're going to 0 really fast, I don't know if you see how fast these numbers are dropping, but it's very quick, right? That's because n factorial is very, very large. which is actually the next point we want to make, which has to do with the growth rate of sequences. And this is the part we really want to pay attention to, because boy, is this going to get used. It's a deceptive thing, right? It seems so simple, and it is, but it's going to be very important to us in chapters 10 and 11.